Alright, in this exercise we're going to use the temperature control lab to understand how sensors measure temperature. So specifically, the temperature control lab has a TMP36GZ sensor. It's linearly proportional to temperature, and here's our relationship, and then that actually is really nice to know. The idea here is that because our system is analog, what actually comes in is some analog signal our sensor will feel some sort of temperature. That's just what it experiences. It's there exposed to the environment. And because the sensor and the dynamics of it, I'll just say physics right now, what comes out is a millivolt response. And we have been able to correlate that millivolt response, or the company that makes the sensors, I should say, has been able to correlate that response with a temperature. And so as we experience the voltage out, we're able to understand what's going on. Just really quick, as far as the physics go, the TMP uses a property that diodes repeatedly change voltage with temperature. And so let's look really quick at the properties of the sensor and maybe answer some of these questions we have for your assignment. So that really quick, the accuracy is within 1 degree at 25 C and within 2 degrees over the range -40 C to 150 C. So let's go ahead. I'm going to copy this information right here, and we'll just go to a new sheet and answer some of these questions. We'll discuss that in just a sec. We'll go back to the Arduino code at the end. Oop, not what I wanted. Cool. So let's talk about this. The first question is, what is the gain, zero, and span? It's a horrible Z. Let's start with gain. Let's go in order. Whenever I think of gain, I think of a conversion from what is going in to what is coming out. So out over in. Now if we think about what's coming in, that's temperature. And the range of temperature is, let's look right here. Have everything in view. 150 minus -40. And the range of associated voltages, let's rearrange our equation real quick. In fact, I'll move all this down. Let's just look at our two equations. Let's make a second equation. And we'll do it in black just to make it look a little bit different. So T degree C is equal to 0.1 millivolts minus 50. So if we're to arrange this in terms of millivolts is equal to T plus 50 times 10. So we're thinking out and in. In is temperature and out is millivolts. So millivolts over temperature is the gain. So if we look right here, it's actually pretty easy. If we think about a point slope, this is a linear equation. The slope is going to be the gain here, where this is a y is equal to mx plus b. This is out, and this is in. That's the one way I think about the slope gain as well as a slope. So let's look at our system now. So we know our gain is going to be 10. But let's look at the range of our outputs as well real quick. So the range, the span is the range. So the span is this denominator, 150 minus -40. That's equal to 190. But what millivolt ranges are we looking at? Well, let's take -40 for example, and if we were to plug that in, we would get a signal of 100 millivolts. If it were 150, would be equal to 2,000. So we have 2,000 minus 100 over 150 minus 40. And let's just think that through. That's 1900 divided by 190, and that comes out to 10 as well. So 2 ways of doing it. They're all derived from the same thing, so that totally makes sense. So we have our gain, we have our span. Let's think about 0 now. So the 0 is the lowest point that we're able to measure of the inputs, and that would be -40. So there you go. Moving on to question number 2. We'll just copy them as we go around. My handwriting's bad enough as it is. We don't need to make it worse. So a millivolt signal corresponds to 25 degrees C. So let's go ahead. We'll use our millivolts equation we had before, which is millivolts is equal to T plus 50 times 10. We'll switch colors. I like switching colors when it's doing something like my work in blue. So let's go ahead and just plug it in. Not that bad. 25 plus 50 times 10. 750. Pretty cool. Next question is 80 degrees C. And we'll go ahead and just do the same thing. We don't even need to rewrite it. We're smart enough. We're engineers. 80 degrees C plus 50 times 10. So it's going to be 30 and then an extra 0. Question number 4. What signal corresponds to a 0.5 volt signal? Let's go ahead and we're going to use our temperature equation now, which is T. I even forgot the temperature equation. T is equal to 0.1 millivolts minus 50. So 0.5 volts is equal to 500 millivolts. So 0.1 times 500 minus 50. So this is 50 minus 50, 0 degrees C. Well, yeah, look at that. And now let's do the same thing. I'll just do 5 off to the right. That seems easier. 5. We have a signal of 1.2 volts. And then we're wondering what temperature that is. We'll do a similar thing. 1200 which is really 120 minus 50, which is equal to 70 degrees C. Finally, we have the last question, 6. That's asking us to plot the current T1, T2 in units of Celsius and millivolts. Let's go ahead, let's just think the equations, how we'll do this one more time. Let's just think through the equations of how that works. Actually, we have our equations. We've done them before. Temperature in terms of millivolts. We'll just write out our functions. But let's do this in MATLAB. So we're going to switch over to MATLAB now. Alright, here we are within our MATLAB notebook. You'll notice we're able to see the answers for each part. So 10 millivolts per degree Celsius is a great way of showing gain. It shows the units. Span of 190 degrees C and 0 of -40. Here we have a function that helps us find the results for each of these, and we'll actually use those. I think that's a great way of thinking of things in life, though, and as you're approaching problems, is thinking of how to make a function to do it once, then after that, it'll do it for you. You'll notice, let's go ahead and we're going to print the temperature, and we're going to also look at it there. So we can see how we're going to approach that, we're going to say a lab is equal to TCLab to connect to our temperature control lab. We are going to read temperature 1 and temperature 2. And finally, we're going to convert it to temperature 1 and temperature 2 in millivolts by using the same equation as before. So let's go ahead. I'm just going to insert the code block. Actually, let's just code right here. Doesn't matter. Lab is equal to TCLab. Let's say T1 is equal to lab.T1. T2. Actually, let's unsemicolon it. I want to see everything. T1 in millivolts by capital V for volts is equal to T1 plus 50.0, be specific, it's a double, times 10.0. And T2MV is equal to the same, T2 plus 50.0 times 10.0. And I like the spacing. So let's go ahead. We're just going to run it again. Live editor, run section. We're connecting to TCLab. Temperature 1, temperature 2, slight difference, and we see a slight difference in voltage as well. So there you have it. Finally, I just wanted to touch on this code example that we have here. This is in C, as it mentions right here. But you can read it just fine, actually. You'll notice we have two constants. So it's we're remembering which pin it is, which is an integer. And if you look at the board, if you slightly pull it apart, you'll see there's those pins that help the Arduino board communicate with the temperature control lab board. We have a float that we initialize for storing the millivolts, and a float we initialize for storing degC. This is a for loop, and in C, for loops work by giving the initial condition. So I is equal to 0, and I is an integer because you have to declare the type. When the conditions for ending, so it's going to go until I is less than n. And then I++ is the thing that happens after each iteration of the loop. So it adds 1 to I each time, is what that means. In Python, that would be I plus equals 1, for example. So the millivolts, which is a float, is equal to the output of analog read that has the input of pin T1. And that times 330 divided by 1024. And where do those come from? Well, if we look right here, the Arduino reports a DL, which is a discrete level between 0 and 1023. But that's in binary. It actually corresponds to 210 discrete levels with a 10-bit code. So that's 2 to the 10th. And then that will be between, the output is going to be a millivolt signal between 0 and 330. So that's where we come up with this gain right here of 330 divided by 1024. We're converting this digital signal to an analog signal. And then the degC is equal to degC plus millivolts minus 500 divided by 10. And then finally, and you think about this, that's similar to before, we had a times 0.1 in our equation up above, but that's all the same. It all has the same units. And finally, degC is equal to degC divided by float n. And then we have a serial where we print line, and that's just printing the output. That's how the C code works. Hope you had fun. Hope that gives you a better idea of how these signals work, and you can use that to help your control.